So here's an overview of the objectives that will be covered in this chapter. I'll introduce the concept of inertia and how you apply that to these types of problems. We're actually going to start by going over Newton's 3 laws of motion. So for some of you, this should be review from other physics courses, but definitely a very important topic to be able to solve these types of problems. And then lastly, to solve for force and acceleration using the method of dynamic equilibrium of an object. So here's some common terms that, just as a review, I've introduced these in previous chapters. So up till now, all of Module 1 has covered kinematics. So kinematics involves the analysis of geometry of motion without the concern for forces causing that motion. So as we saw in our last chapter, we really focused in on both linear and angular motion combined for planar motion. To be able to solve for velocities. So we had two different methods, right? We had relative velocity method and the instantaneous center method. So moving forward now, we will be looking at the study of kinetics, which is the study of motion and the forces associated with the motion. So as we had a couple of chapters ago, we included analysis and calculations for acceleration of bodies based on a rate of change from velocity, right? So now we're looking at throwing in forces. This acceleration that is produced due to a force. So what kind of a force? How is it applied? And we'll look at that specifically for linear motion in this chapter. The last term is a particle. So particle, again, is a body with a mass but negligible size and shape. So while you will see that I'll be discussing, talking about, say, a box or a vehicle or various different objects that typically do have a shape, for the purposes of the calculations that we'll do, even though these do have shapes, we're not really concerned about those shapes. So we'll assume that if it has a mass, it is a point mass, and that when you apply a force, it's applied to that point, to that point mass. And so obviously things like torques, where you have a force applied offset to the center of gravity, will not be taken into account in these types of problems. Okay, so this brings us to Newton's 3 laws of motion. Starting with the first one, we have an object remains at rest or maintains a constant velocity in a straight line unless acted upon by an external unbalanced force. Now, for a problem like this, what I'm really getting at is, we'll take an example here with a box. Okay, so we have this box and we apply an external force. Okay, we're going to call that force F1. So we apply a force, and what would you imagine would happen when you apply the force to this box? Well, obviously, if you apply enough force, this box will begin to move to the right. So we're actually going to see a velocity to the right and do that force. In fact, we will have an acceleration as well in that direction. Now that's an external unbalanced force. So what exactly does the term unbalanced force in this case mean? Well, let's look at another example with this where we actually add a second force, and we're going to call this force 2. So imagine yourself, they're pushing against a box, and you have a friend who's pushing on the other side of the box. Well, if you're both pushing with the same amount of force, obviously that box is not going to go anywhere. There are external forces, but there's no unbalanced force, meaning those forces basically equal out to each other, or cancel out to each other. So as a result, that object remains at rest. So in this case, the box remains at rest. It does not move. That's what we mean by an unbalanced force. There can be multiple forces. It doesn't just have to be one. There can be any number, an infinite number of forces that are applied to the object. But it's about the fact that it's an unbalanced force that allows it to actually accelerate in a given direction. All right, moving to number 2, Newton's second law, F equals ma. What I typically like to show this as, I show it as a sum of forces equal to ma, just for the reason that we discussed in Newton's first law, is that it's an unbalanced force. And so what you want to do is you want to do all the sum of the forces, and we set that equal to ma. It's a pretty straightforward equation. You would have likely seen this before, where a is equal to the acceleration, mass per second squared, and meters per second squared and feet per second squared. Our force is equal to newtons and pounds, and then our m for mass is kilograms and slugs. And don't forget, again, that mass, the units for mass in US standard units, that's slugs. Okay, if you are given an object mass, but it actually gives it to you in pounds, well, that actually is not a mass. That is a weight, and as a result is a force. So you have to just be very careful of that when you are looking at solving these problems. Okay, so in other words, this means that a body with an external unbalanced force behaves as follows. A is proportional to F. So I like to write this out as follows. So A, and that is the symbol alpha, so can also be used to designate proportionality. So A is proportional to F. So what does that mean? It means that as A is increased, F is increased as well. And since they're directly proportional, it means for the same amount that you increase A, F will also increase. So if you double the acceleration, you'll double the force. Or if you double the force, you'll double the acceleration. A is in the same direction of the resultant F. So as we saw or see in the figure above with the box with an external applied force, if I remove force 2 here, then what will we see? We will see that the box accelerate to the right in the same direction than that the external unbalanced force is being applied. And lastly, A is inversely proportional to M. So how would I show that? I'd say A proportional to the inverse of M. And so what that means is that as A is increased, then M is decreased. Or if M is decreased, then A is increased, and vice versa. So they are inversely proportional. Just something to keep in mind when you are solving problems. Okay, last but not least, Newton's third law of motion. For every action or force, there's an equal and opposite reaction or force. So, you'll often hear that term for reaction. There's an equal and opposite reaction. In this particular case, we're talking about actual forces, right? One example, when we go back to this box here, we can assume that there is a weight, there's a mass, and therefore, because of gravity, there is a weight being applied from that box onto the ground. Well, whatever force is being applied from the box to the ground, we have a force equal and opposite. So therefore, the ground is applying a force to the box with equal magnitude, just opposite in direction. And what is that weight? Well, very simply, remember that F is also equal to mg, g being the gravity here on Earth, right? So acceleration due to gravity. So G is equal to 9.81 meters per second squared. Or if we're dealing with US customary units, we can say that G is equal to 32.2 feet per second squared. So do remember that it depends on which units that we're working with, okay? Very important here. Okay. So this brings us to the concept of dynamic equilibrium, which really is, I guess the short of it would be to say that we want to take our dynamic problems and make them very similar to what you do in statics. So in statics, forces are being applied. That's why we do our free body diagrams. And in our free body diagrams, the forces have to balance out, right? that's kind of what we want to do here with dynamic equilibrium. And there's a way to do that, and that's what we're going to talk about here. Typically, there's two methods for dealing with inertia and acceleration for linear motion problems. The first you most likely have seen, and that would be the sum of all external forces. So you sum up all the external forces and you equate it to mass times acceleration. So what do I mean? I mean, if you take the sum of the forces, we just set that equal to ma. So again, we draw that box that has a mass, and we apply an external force, external unbalanced force. Then we know that that box moves in that direction with an acceleration. And how do we solve for that acceleration? Well, we just rearrange our equation. So where we have the sum of the forces equal to ma, we rearrange it for a, and a is equal to the sum of the forces over mass. Okay, so a very standard way of solving these this type of problem. However, in the textbook, you're going to see it's done a little bit differently. And the way they do it is through a method called inertia force method. And really, it is essentially the exact same thing. Here's the difference. Instead of stating F, the sum of the forces equal ma, we're just going to move that term ma over to the other side. So we have the sum of forces minus ma equal to 0. So that really is it. Okay, as simple as that. You'd say, well, what's the point, and why would we be doing that? Well, it's just a different way of thinking about it. So mathematically, no, it does not make a difference. However, it is a way to think of this inertia term. Inertia, what is inertia? Inertia is the force that wants to keep the body doing opposite of what the external force is trying to do. So say you're sitting down and somebody's trying to push you, right? Well, your inertia is opposing that force. It wants to try to keep you still. Okay, so that's all it is. It's the opposing. That's what inertia is. It's trying to oppose that force. So if we draw that out, it's just going to look slightly different from the previous problem. So we have a box with a mass, and we're applying an external force. Okay, so it has a reactionary force. It always acts in the opposite direction to that externally unbalanced force. So in this case, it is to the left, since the external unbalanced force is to the right. We're going to set that equal to ma. We know that the direction of acceleration of the block will still be to the right because the external unbalanced force is to the right, and the acceleration must follow that direction. But the inertia term is always opposite to that. So when we're creating our free body diagrams, if we know it's going to move in a certain direction, then we always essentially we just apply an extra term, that inertia term, which is ma for linear motion, and it is applied in the opposite direction to that external unbalanced force, as we see here. Just a little bit different, and I hope it becomes a little bit more clear once we go through one of our first practice problems. So just as a summary for dynamic equilibrium, inertia of an object tends to maintain the present state of the object. It really does oppose the change. Okay, so inertia opposes the change. Inertia force is equal to ma. So that's not ma, that is the term ma. When we're dealing with linear motion, it is ma. And will act in the opposite direction to the acceleration of the object. So whatever direction the object is accelerating, the inertia force acts in the opposite direction. Using this method, the object is shown in a state of dynamic equilibrium, as we mentioned, very similar to what we would see in our static problems. So the free body diagram can therefore be treated as static equilibrium, a free body diagram. Okay, so that brings us to the next set of forces that we need to think about when we're solving these types of problems. and that includes frictional force. So remember, you're pushing this block along the ground. What is opposing that force? Why doesn't it just move easily? Well, because there's friction, right? You're trying to push a box on carpet that has a high frictional force, or a coefficient of friction really is what that would have, is a higher value there. It is a lot more difficult than to move, say, on wood, right? Like a smooth or a shiny surface, wood or ceramic. Much more difficult to move on carpet. Why? Because it has a higher coefficient of friction. So we need to include this force in our free body diagrams. How do we express this? Well, it's shown as follows. F sub F, for frictional force, is equal to mu being our coefficient of friction, times the normal force. So you'll either sometimes see it as N, or also written as F sub F equal to mu, and then just another force, which is F sub N for normal force. Okay, so you will either see it with a large N or with a large F sub N. I'll often use the second term here, so you will often see me use this term here when I'm solving problems. So again, our frictional force will obviously be in newtons or pounds, normal force in newtons or pounds, and coefficient of friction, which will be some fractional number that is given. Now, I will mention it when I go through problems with it, but often the book will tell you what the kinetic friction is, coefficient of friction is, but it sometimes will give you a static coefficient of friction. Now, the difference between those two are very, very small. Basically, when it gives you a static friction, that is the friction when the object is not moving. Whereas a kinematic or dynamic friction is given, that is when the object is in motion. If you ever tried to push, for example, push a box or push an object along a surface, you'll notice that when it's first starting out, it's a little bit harder to push it just to get that motion started. But as soon as it starts moving, it actually feels a lot easier after that initial push. And that's the difference. That's the difference between your static, when it's not moving, versus dynamic coefficient of friction. Okay. For an object that is pulled or pushed horizontally, the normal force is often given as N equal to mg, or if I'm using that second equation up there, that really is just this, Fn is equal to mg. Now you'll say, okay, well, what do you mean? Well, remember this, as I mentioned a couple slides ago, when we're dealing with, so I'll just draw a box again. And this box will have a mass, right? So if we wanted to figure out the weight of that box, which remember weight is a force, we would say that weight is equal to mg, where g is equal to the acceleration due to gravity, 9.81 meters per second squared, or 32.2 feet per second squared. So I would apply that downwards on this object. However, as I said, that force that is being applied, it's not actually being applied on the object. In fact, if I were to erase this, really what that is doing is it is a force that is being applied from the box object to the ground. And as a result of that, there is a opposing force. So where that downwards force is the weight, then technically that normal force acting on the object is our Fn. Okay, equal but opposite force. Okay, you'd say, well, I don't understand, why are there two forces there? Well, if this object has a weight, which it does, it has a mass, therefore it has a weight, it is applying a force. Well, we know that if there's a force being applied, an external unbalanced force, if there's no other forces acting in that vertical direction, then that object should be accelerating downwards. But intuitively, we know that's not happening. Why? Because the object is sitting on the ground. It's not going through the ground, is it? Well, why not? Well, that's because we have this opposing force. So these forces cancel each other out, and therefore there is no acceleration in the vertical direction. Okay, so just something to keep in mind there. Okay, so we're not going to cover pulleys and tension today. I think what we'll do is just to start things off here, since we are trying this out for the first time, I'm recording this video for you, probably talking a little quicker than maybe you're used to, or just, you know, the fact that I'm not in the classroom with you. So what I'm going to do is I'm going to go over one practice problem with you. And then I'm going to give you the opportunity a few days this week to do some practice problems based on this first problem that I'm going to go through, and then sort of leave it open for you to ask any questions. And then by the end of the week, I will post a follow-up video showing you how to solve even more complicated problems, and then eventually get to the next topic, which would be pulleys and tension in this chapter. Okay, so I'm going to add a page here and going to try 13.1. So this is not the example problems that are worked out in the chapter itself. This is at the end of the chapter on page 456. Okay, so I'm going to do this. What I would suggest you do is try examples. So these are the examples that are in the chapter. I'd like you to try 13.1 and 13.4. Now those solutions are worked out for you in the chapter, but what I would suggest is read the question first, and then without looking at the solution, try those questions on your own. After you've gone through this video, do those, try them out, and see how well that works for you. If you're having a great deal of difficulty, the solutions are right there, so look at that. And then if things still don't make sense, then what I would suggest is that you contact me. And what I'll do is I will be looking over the next couple days sort of a platform that we can use to sort of get instant feedback, whether some sort of webinar, either FaceTime or something that'll work, kind of work for everybody, where I either do one-on-one or we work, even as a group. Multiple people want to sign in at once, and I can maybe try to work out problems kind of live with you. But for right now, I want to try this out and see how well this goes. So. Okay, so let's go through practice problem 13.1. The question states, determine the acceleration of the 150-pound block in figure P13.1 if the coefficient of kinetic friction is 0.4. And there is a figure that is attached to this, so I'll draw it out here. And we're dealing with, a box. And this box has a weight of 150 pounds. So this is one of those questions where, you're used to seeing maybe mass showing on here, but this is not a mass, this is a weight because it's pounds. If it was given to you in slugs, then you know that would be a mass. So I'm going to also show the forces. So we have a force here of 60 pounds, and it is applied at an angle of 30 degrees. And then we have a force applied on the backside of 90 pounds, and it is applied at 45 degrees. Okay, and all right, I think that's everything. The only other thing that's given is that we have a kinematic coefficient of friction of 0.4, and they would like us to determine the acceleration of the box. Okay, so I mentioned as I was going through all of these forces that we have to consider when we're solving this problem. And then I said, well, we have to do this sort of the sum of the forces equals ma, but that ma is really inertia terms. So there's a lot of stuff kind of going on there. So the easiest way to break this down is just as we do with our projectile problems that we did in previous chapters. In those problems, I always told you can't just solve for velocity when the velocity is acting at an angle, right? We have to break it up into components. So that is exactly what we're going to do here. We're going to break it up into x and y components. Now, keeping in mind that when we're trying to solve for the frictional force, so if I just go back here, we said that the frictional force is equal to mu, the coefficient of friction, which is given, and a normal force. That normal force is a vertical force. And so in order to be able to solve for the acceleration in that x direction, we are going to need to solve for the vertical force first. So let's start with that. So we're going to look at first the y-axis. And then over here, we're going to look at the x-axis. So we're going to do two free body diagrams. So in the first diagram, we have our mass. Second one, again, we have our mass. Okay, and we're going to show all of the external forces. So vertically, we have 150 pounds. Now remember, that is a weight, and so that is a force being applied vertically in the downwards direction of 150 pounds. We have a normal force. Remember that that normal force opposes the weight, so acting vertically. Now it's easy, and some people forget or think this right away, that it's equal to mg. I did give that equation, and I said that normal force is equal to mg. That is true. However, when you're solving this, remember this is for static equilibrium. It's true if there are no other external forces being applied, right? Because 150 pounds is acting downwards, but we have two other forces. If either of those forces have a vertical component to them that is acting downwards, then in fact the weight is more than just 150 pounds, isn't it? So let's look at that. Let's break up our two forces into components. So if we looked at the 60-pound one, we would have a horizontal component going to the right, and then we would have a vertical component going up. And then for the 90-pound example, we would have a vertical component, in this case going down, and then a horizontal component also going to the right. So we'll need to include those two vertical components. We have one going down from the 90 pounds, one going up, of course, from the 60 pounds. Of course, they're not just 90 pounds and 60 pounds, they are components of them. We do have angles, so we can easily figure those out. We would say that based on the 60-pound force, its component would be not 90, it would be 60 sine 30 degrees, while the other side would be 90 sine 45 degrees. Right? These are just right angle triangles, and so the sine would be using the opposite here, opposite of that angle, which gives us the value. Okay, so that's all of the forces that are in here. We also want to make sure we are specifying what we consider positive, so I would say to the right and up would be our positive directions. So let's do our sum of the forces. Sum of the forces in the y is equal to 0. Remember, we're not doing sum of the forces equal ma, we're technically doing the sum of the forces minus ma equal to 0. However, because there will be no acceleration in the y direction, why is that? Well, because it's sitting on the ground, right? It's not going through the ground, or it's not going to float. So therefore, the inertia term is 0. So no inertia term. Okay? And that's why that ma goes to 0. So we just have the sum of the forces equal sum of the forces equal to 0. Okay, so sum of the forces in the y equal to 0. So let's add them all up. So for positive ones, we have Fn plus 60 sine 30 degrees. And then we're going to subtract 150 pounds minus 90 sine 45, and that equals 0. So we don't really need to rearrange anything. Well, we just basically simplify and then solve for Fn. And Fn, you will find, is 183.6 pounds. So there is our normal force. Okay, so that doesn't give us our solution for acceleration, but it's going to allow us to solve for our frictional force, which would then give us a head start solving for acceleration in the x direction. So let's, using what we did in in the y-axis, let's do the same thing in the x. So we know we have a component for the 60 pounds, and so that would be 60 cosine 30 now. Similarly, we also have a 90-pound horizontal component, so this is 90 cosine 30 degrees. We have a frictional force. Now this frictional force, it does not, we have to be careful here, it does not oppose the acceleration, it just opposes the direction of movement. And that's a very fine line. And I will talk more about that when we get into more of these types of problems. But remember, the inertia term always opposes acceleration. The frictional force just opposes the motion. Why is that important? It's important because acceleration can be positive or negative. So even though this box is moving to the right, you can have an acceleration going to the right or the left, even though it's actually moving to the right, right? That's accelerating or decelerating. So again, your inertia term opposes the acceleration, whereas the frictional force just opposes the actual motion of the object. So that being said, what are those two terms? We're still missing those two terms. So for frictional force, we assume we have two external forces going to the right. That means we should assume then that it is accelerating to the right. If it's accelerating to the right, that means that we have an inertia term, ma, acting to the left. And we also have, same thing, but a frictional force acting to the left. And that would be mu k times Fn. So there are our four different forces. So let's do the sum of the forces. I'll do that in black. So the sum of the forces in the x is equal to 0. And we're going to include that mass term in there, mass and acceleration. So we add them all up. Again, we're going to assume to the right is positive. So we're going to go 90 cosine 30 degrees plus 60 cosine 30 degrees. And then we're going to subtract our mu k. So mu is 0.4. And our, so mu k times Fn, which is 183.6. And then we're going to subtract ma. And we're going to set this all equal to 0. So ma is the term we want to solve for, but really what we want to solve for is a, and more specifically ax, right? The acceleration in the x direction. So the question is, do we have a mass? That really be the only thing that's missing here, right? If we have the mass, then we can solve for the acceleration. Well, the mass is not 150 pounds. Remember, that is the weight. But if we take our equation, weight is equal to mg, we can see that we can rearrange for m, right? So therefore, m is equal to the weight, which is 150 pounds, over, I hope you said 32.2 feet per second squared, because we are dealing in US customary units. So now what can we do? Well, we're going to take this value for m, and we are going to sub it in here. And then we're going to solve for ax. So let's do that. So let me, I'm just going to simplify. So 90 cosine 45 is going to give us 63.6 pounds. Plus 60 cosine 30 is 51.96 pounds. Minus our 0.4 times 183.6 is 73.4 pounds. And when I bring MA to the other side, we have 150 pounds, which you can simplify as well. I just didn't do that here. 32.2 feet per second squared. And we're multiplying that by AX. So what can we do? We take the left-hand side, we add all those up. and then we divide through by that weight term, the 150, or the mass term, sorry, 150 pounds divided by 32.2 feet per second squared. You do that and you get a value for acceleration, and that is 9.04 feet per second squared. Okay, and that is the final answer. Now, that being said, acceleration, as we learned before, is a vector, so it has magnitude and direction. So make sure you include the direction. In this case, it is to the right.